Hello. It's late in the day. I'll keep it as short, sweet, hopefully leave lots of space for questions. Today, I really want to dive into kind of this big problem I run into over the past 6 months to a year of working with streaming platforms, and that they're all essentially the same, right? Like in the open source world, you have 12 or 13 or 14 frameworks now, all at first glance look fairly identical, and it's actually kind of hard to distinguish what they're really doing under the hood until you really dive into it and understand it. And the reason this matters is when you're building a product, right? When you have a concrete problem that you want to solve, you're going to have a unique set of requirements. And each one of these streaming frameworks that's out there solved a particular problem for the people that build it. And whether it solves the problem that you have at the present state of time, right, that's kind of an open question. And so my intent with this talk is to kind of highlight how I think these frameworks actually distinguish themselves, and in kind of the engineering world where you need to build a system that will run, that will be stable, and where you've kind of considered the whole of what you're building, that there's really a few key things that you can look at to differentiate these. So minor addendum, Data Innovation Lab, at Capital One, also known as Vault 8, we're essentially an R&D team. We go out, play with all the new tech, involved heavily with open source, and then ultimately bring it back to tackle concrete projects within the business. So that's kind of the genesis of all this investigation, understanding, what have you. So firstly, kind of very quickly, we're all here, we're big data folks. I'm not going to spend a ton of time on this, but there's kind of a fundamental distinction between batch and streaming, and really the big thing in my mind is that how these things are built around is really a function of latency. They both are going to process large amounts of data, as we call it, but the timescales that you're dealing with in streaming systems are going to be on the order of milliseconds and microseconds, rather than seconds, minutes, and hours. And this is really, in my mind, what distinguishes the true streaming platforms from things like Spark Streaming, where they microbatch and under the hood. And really, you're dealing with a batch platform, even if it says it's a streaming platform. So quick examples: MapReduce, Spark Tez on the batch side, Storm, Flink, Apex, KafkaStreams, GearPumk, Concord, AkkaStreams, pick your run-of-the-mill. We had, the new one presented just now. Heron as well, but not open sourced yet. Four key things in my mind that really do matter when you're talking about these things. And there's kind of fundamental questions that we all ask, and it's how do we handle more data? How do we handle that data quickly without ever losing data or compute? And this one is huge, right? Like how these frameworks solve this particular question turns out to be a key differentiator. And then kind of a slight nuance on that, how do we ensure these systems keep working even if there are failures? And these are these four concepts, right? Scalability, performance, durability, and availability. And each one of these has concrete metrics associated with it. For scalability, we're never going to get true linear scaling. The idea is, right, we can add 10 more nodes to double our cluster size. We're not going to see a 2x increase in performance. We might see 1.5x if we're lucky. As close as we are to linear, that's the best that we can hope for. For performance, I'm talking about throughput and latency, right? These are hard numbers. For durability, I'm talking about loss of data and loss of compute. Can messages be lost? Can we lose state? These are kind of key questions. And lastly, availability is for everything that comes in, for every request that the system receives, will it generate a response? And this turns out to be kind of a key differentiator when you go from the toy land of prototypes and fun problems and exploration into actually building a product that works, and especially a product that works at scale. And the thing is that all of these are kind of intimately connected. You can't look at any one of these in isolation when you're either analyzing a system or when you're building a system. And that's because there's really these trade-offs, right? And concretely, if you focus on scalability, right, making systems that will run larger and larger and larger, then first of all, you're going to have challenges with durability. The more moving pieces you have in your system, the more room there is for something to break. You're going to struggle with availability because there's more things to keep track of. If you have more things breaking, that means you have to be more resilient to failures. You're going to struggle with performance because when you have more components of your system, you're going to have bottlenecks, you're going to have challenges with synchronization, consistency, you name it. On the flip side, if we focus on availability, then performance is going to be harder to guarantee. When you want to ensure that your entire system stays operational, you're going to be dealing with the overhead of monitoring and synchronization. You're going to have challenges with scalability because, again, these are kind of contradictory concepts in some sense. And you're going to have challenges with durability because recovering without losing data means that your system has to be even more robust. And lastly, durability kind of suffers for the same all the above reasons. Now, in the batch compute land, they have it easy, right? You get scale out in performance because you can add hardware and you can simply take longer. Because the time scales that we're dealing with are different, we can actually, most of the time, just get around the challenges of scale out by throwing more hardware at the problem. And that was kind of what happened with MapReduce, what happened with Spark, right? The bigger your cluster is, things just magically start working. You get durability when you use a stateful backing store. MapReduce and Spark, they're ultimately based on top of HDFS or S3. You know, they're on disk, they're on a physical disk. If you cut power, that data's still gonna be there. That data's still gonna be replicated. In a streaming system, you don't have that luxury. You can't have this recompute because that data is in flight, it's never landed. You get availability because the timescales that you're operating on are longer. If you're running on Yarn, Yarn will restart a process in 30 seconds. In batch compute land, that's a very small amount of time. In the streaming world, that's an eternity. So kind of the crux of this is in the land of stream processing, you don't have this time. You don't have this luxury of being able to wait for something to recover, wait for your system to read data back from its durable store or your Kafka to get back to an operational state. So it's really not about performance and scale. If you look at all of the streaming frameworks out there, most of them are going to have numbers akin to, they're going to process 1 million transactions per second per node, or they will have latencies on the order of tens of milliseconds, right? That's not what sets them apart. And these things will run on 1,000-node clusters. Storm, for example, does great. But the challenges that you run into are kind of these 4 things that I laid out here as I see it. The first is ease of use. And when I say ease of use, I literally mean how quickly can you build an application that's more than a toy problem. I don't care about word count. Word count doesn't help you solve a real challenge. I'm saying a legitimate production application with all of the intricacies associated with actually running something at scale in a distributed environment. To get to the point where you can legitimately hand it off and say, hey guys, I have a product, it will work. If things break, it will recover. How easily your framework provides you the ability to do that turns out to be a quick key differentiator. Bringing us to the second point, and that's failure handling. What happens when things break? In a distributed land, things are going to break. So what does your system do when that happens? Does it handle failures by sacrificing something else? Right? Can your system be resilient to failures without sacrificing throughput or latency or availability? For durability, how do you avoid losing data without sacrificing performance? Same idea. And for availability, this is really kind of getting into DevOps land. How do you keep the system running with a minimum of manual effort? Because at the end of the day, there will be a person that has to restart a failed process or restart a failed node. And the more people that you have in the loop, the more room there is for error, the more room there is for this process to take longer, and for things to never recover fully because of things like a cascading failure. If you have a system that recovers on its own, you have a much more robust solution. So, next, I want to just look at 3 particular technologies. And these aren't selected for any particular reason aside from the fact that I'm very familiar with these. And I think that they highlight a lot of kind of the key issues associated with streaming technology in general, right? Again, I spoke to kind of a lot of these things being similar. Many of the concepts that I'm going to talk about today will generalize. You'll see the same things when you look at how KafkaStreams works, how AkkaStreams works, how GearPumk works. There's a lot of similarities there. So we'll look concretely at Storm, Flink, and Apex, and look at how they deal with these 4 things that I listed. So first, we've got Apache Storm. And Apache Storm has been kind of our dinosaur. It's been around forever, works really well. Twitter ran it forever on massive clusters. It was scalable, right? 10,000 nodes. It was performant. You could run Storm fairly easily at single millisecond latencies, and it was easy to use. You can stand up a Storm cluster on a machine or on a distributed environment fairly quickly. You can write applications in a fairly straightforward manner once you wrap your head around the idea of creating topologies for passing around data. But it had a number of weaknesses. If you were Karthik's talk earlier on Heron, he dived into some of these. But essentially, failure handling compromises performance, and it compromises it in a very kind of drastic way. I'll dive into that in a second. The second bit is that keeping things running at scale in a production environment turned out to be a major challenge. There were a number of challenges around resource sharing, scheduling, reliability, dynamic application deployment, things that you need when you want to keep something running over a long period of time. And the last bit is kind of flexibility, which ties into this notion of building dynamic reconfigurable applications that are easy to modify and easy to adjust to whatever use cases you run into. The last bit's kind of an open question. I'm not going to stay up here and say it. There is a lot more noise in the big data community about most other technologies. You don't hear much about Storm anymore. Storm is still running in many companies. There was, at the same time, a major patch that just came out for Storm 1.0 that added a lot of features that have been missing over a while, and Hortonworks is definitely still selling it very hard as its streaming platform of choice. So I'll leave that up to you. So in Storm, very simply, most of you have probably seen this in one form or another. You've got spouts that emit data. You have bolts that consume data. They pass data between each other. Bolts are logical operations that transform your data in some fashion and emit it to downstream consumers. And you can obviously have multi-input, multi-output connections. Concretely, you've got kind of different ways that you can pass around data. These groupings aren't super important. Essentially, this is just getting at the idea that you can do a lot of things in parallel. In Storm, you achieve scalability and parallelism by applying the same logical operation to different physical pieces of data. So if you have a vector of data that comes in, that vector of data will be physically partitioned to multiple nodes doing the exact same thing to the data, and then passing it downstream. Now, what you wind up with is a graph ultimately that looks like what you have on the right. Data is passed back and forth between nodes. In Storm, these nodes are actually separate, often separate processes. This is not a configurable thing. Storm will kind of deploy operators and bolts and spouts where it has the resources to do so. When we talk about Apex later, we'll see how being able to configure this programmatically can actually help you build more robust applications. So what happens when you have a failure in Storm is that the upstream provider, the spout, will emit data, and then it will basically wait for a response from downstream saying, hey, I've got the data, I've processed it. And the only way that you can do this is if you have a heartbeat, right? You're essentially saying, hey, are you done yet? Are you done yet? Are you done yet? At some point you time out, say, well, I didn't get a response. Well, what am I going to do? The problem is that there's no way to do this in Storm any quicker than 1 second. There's kind of a hard limit on a minimum act time. And you can get around this problem if you kind of say, hey, well, okay, I'm gonna parallelize my system. I'm gonna do the same thing in multiple parallel pipelines, all doing the same operations to the data, but that way if one of my pipelines fails, the other two will still succeed, and I'm guaranteed to at least have one output at the end. And if I'm okay with at least one's processing, or I have something downstream that can take the first response out and say, hey, I'm done, this is an acceptable solution. Now, the problem is that in Storm, when you have this failure, if you have a bolt that fails downstream, the problem is that errors propagate. The only way that Storm can reset its state and recover and replay what it ran into in the case of a failure is to actually reset the spout and resend that message again. And the problem is that this resets the entire topology. Now, this issue of cascading failures makes it harder to create a program like what I just described, where you have these independent pipelines. And what this means is that instead of building a single application that can deal with failures, the only way that you can get around this is by deploying multiple applications. But then you run into the complementary issue that Storm's not very good at running multiple applications simultaneously at scale. This is kind of diving into the fundamental challenges that Twitter ran into with Storm and why they built Heron. So it's kind of, a chicken and the egg problem. And there's a number of other weaknesses with Storm. The big one is, this recompute on the entire tree. It's hard to debug because operations in individual operators are shared, right? You might have multiple logical operations within the same JVM, and that means that you can't isolate individual processes. A big push within Heron was to actually separate everything into individual tasks and processes so that you could see and pinpoint where anything failed, and also to, again, isolate failures so that they don't affect other components. And the last bit is this kind of getting into this notion of dynamism, right? If you want a living, breathing environment that you can change and adjust to solve your needs, then you want to be able to have dynamic topologies that you can modify and reconfigure in flight. You want to have dynamic scaling, where you can increase the parallelism of your system to handle more data. And you want to be able to add and remove applications without service interruption. And Storm does not have many of these things, even with the recent 1.0 release. So let's look at a second example. Let's talk about Flink. And Flink hasn't really positioned itself until very recently as a streaming competitor, but now they're kind of pushing on this very hard. For a long time, they were kind of ganging up on Spark. And this turned out to be a really brilliant move because everyone was talking about Spark, and as soon as Flink came along and said, hey guys, I'm the next Spark, everyone started talking about Flink. And Flink did one thing super well, and that's that they started with a declarative high-level API, right? The one thing that makes Spark most successful in my mind is that it's easy to use. And Flink took the same approach. It's got the same notions of map, reduce, filter, join, group by, and you write applications really simply. Under the hood, Flink will make the same kind of topology that you are manually configuring in Storm. But what this means is that your kind of time to functional application is a lot lower. Now, what it also brings to the table is, like Storm, it's a true streaming platform, right? It is legitimately processing data one piece at a time. It's not doing microbatching under the hood. Technically it is, but that's for the sake of network efficiency, and it's a configurable thing. And the guys did a really brilliant thing in that the folks that built Flink were actually database engineers. And so they built in a really kind of powerful query planner that goes a step further than what Spark does, where they kind of collapse the DAG as much as they can to minimize disk reads. They will actually compute the optimal DAG for a given set of operations that you present, making it easier to build more efficient applications. And the last bit that's kind of really in favor is this notion of community, right? So Flink has a very fast growing presence in amongst meetups, amongst conferences, and that turns out to help a lot, primarily because it gets more people involved and more people contributing, and open source projects succeed based on how well they interface with each other and how much excitement and activity there is around them. This kind of whole environment really depends on the feedback and interaction that people have with each other. So succeeding there makes it much more likely for your project to succeed in the long term. So to that point, right, how does Flink work? Same basic idea as Storm, except you're no longer talking about individually configuring where data flows in your system. You're actually just saying what you want to do to the data. And Flink figures out how to transform that into a graph. Now, the next bit that's interesting is how Flink handles failures. Instead of the Storm approach, where you have to have something upstream, produce data, and then wait for a response to come along that it can acknowledge as having been processed, what Flink does is they inject these markers into the streaming data. These are treated like any other piece of data, with the exception that anytime an operator sees a barrier, it says, hey, okay, I've processed all the barriers that came before me. I'm going to save my state. And Flink does this in a distributed fashion. So every operator will write to a distributed store lying underneath, and it'll do so independently. And what this means is that Flink can both serialize its state and then recover its state really quickly without the additional overhead of having to wait for a problem to come along. And the most that it ever has to roll back is to the previous barrier. And these can come along at configurable intervals. Now, the advantage of this is that if you kind of write sensible applications that don't abuse the amount of memory that you're storing, or the amount of data that you're storing in the memory of each operator, and then there's not a lot of state to serialize, this is a really lightweight process. And they have some excellent benchmarks in their blogs showing this comparison with Storm of even in failure scenarios, we still keep running with more or less the same throughput and the same latency as we would in a scenario where we're just dropping failures on the floor and not recovering. And you'll see that Storm will do terribly, right? Like Storm will have an immediate massive performance degradation, whereas Flink will just keep running fine. Now, more on kind of the differences with Storm is that Flink handles kind of planning and optimization for you. You don't have to come up with your optimal DAG. The lower level internals are abstracted, which is coming back to this ease of use idea, right? How do I quickly write complex applications that just work? Another huge thing is that Flink has clear semantics around windowing. If folks have been following kind of the discussion around Beam, which is the notion of building a unified kind of API around streaming platforms, this is one of the key things that you have to have. How do you deal with out of order data? How do you know when all the data you wanted to process has arrived? Flink has that explicitly defined, and they're actually the first project, open source project outside of Google that has actually implemented a fully Beam compatible, or a mostly Beam compatible implementation for a streaming platform, I should say. Failure handling is lightweight and fast. And another big thing is that in the Storm world, because of this acking mechanism, there's actually no way to guarantee exactly one's processing, because the downstream operator might have succeeded, but it might have just taken too long. So the only way in Storm to guarantee exactly one's processing is to use the Trident framework, which essentially forces a micro-batching on top of the underlying Storm API. In Flink, you can get an exactly once guarantee as long as you have a connector that deals with a stateful database or data store upstream that can actually do this kind of ACK response that says, hey, I'm gonna have written everything up to this checkpoint, and the database can say, that's right, you've done that. So something akin to a Kafka, right, where you know how far you've consumed in your buffer, except just on the output side. And kind of this very, very nice thing at the end is that Flink will actually run Storm applications natively, which means that if you have Storm topologies already written, then you can migrate to Flink transparently and it'll just work. So what can't Flink do? Flink still cannot dynamically update its topologies, and it also can't dynamically scale out to deal with more data. These are still kind of static things. The other big thing is that Flink cannot recover from errors without stopping the entire DAG. In the same way that Storm had to roll back all the way to the source in order to recover from failures, Flink has to do the same thing. Flink does it faster and more efficiently, but it still depends on an upstream durable store from which to recover, something like a Kafka or a stateful repository on HDFS, in order to recover its state and replay all the messages that were not processed from the last received barrier. It also can't give you kind of fine-grained control over how data moves through the system. And when we talk about Apex, we'll see why this matters. But the thing is that this high-level API, right, this ease of use, this isn't always a good thing. It's kind of like a hidden curse in some sense. And Spark runs into the exact same thing. That on paper, Spark is super easy to use. It's easy to write complex ETL pipelines in Spark until things break. And when things break, then you really have to dive in and try to figure out, hey, why did things break? And then this high-level API that made it really easy to write this application turns out to be something that just gets in your way because you can't decompose it and actually fix the things that you want to have control over. And the last kind of question with Flink is really, can this thing run in production? Very recently have they started to announce their first production customers. And this really matters ultimately when you're trying to come to the business and say, hey, I have this new technology, I want to build critical infrastructure on this technology, and you want to be able to point at something else and say, these guys did it, right? That's a huge selling point for Storm. Storm runs. There are production environments running Storm. There are applications on top of Storm that run reliably and stably. You can point to those and say, hey, they did it, so can we. With Flink, you kind of can't do that yet. And this makes it harder to kind of get buy-in for whatever you're buying, for whatever you're building. And you can't do anything alone. So there's a lot of other things out there. There was a blog that came out about a month ago. A guy basically printed out a chart of open source streaming technologies and compared them against a number of criteria. He missed a bunch, and I think 3 or 4 more came out since he did that chart a month ago. So there's a lot of competition, and there's a lot of kind of similarity between these two. Which are kind of the interesting ones? In my mind, there's 3. The first of these is Apache Beam, and that's because A, it comes out of Google, which means that there's going to be a huge amount of excitement and interest because Google has been traditionally kind of a closed shop, and by the time that they release something to the rest of the world, they've already moved on and they're building something else. This is kind of the first time that Google is releasing something that they're actively soliciting involvement and contribution from the community. So it's really kind of their first, I would argue, real foray into the open source world. And the notion with Beam is that it's not a streaming platform in its own right, but it's a way for people to unify all the streaming platforms that they may want to use for their use case under a single API. So if there are some things that Apex does well, and some things that Storm does well, and some things that Flink does well, you can literally use them interchangeably because you know that they're all Beam compatible. And once you get sufficient momentum with this kind of approach, this becomes super powerful, right? It's essentially defining a standard for streaming. And that's a really great idea. The next bit is Apache Apex. And that's up here because, in my mind, of all the open source frameworks that are out there, it has the most robust architecture, and it solves the problem of durability and availability in the best way. And the last of it is IBM Echoes for your streams. Now, this bit here is not open source tech. I lost my mic, I apologize. This is not open source technology, and in fact, it is extremely expensive technology, but it is also pretty much the gold standard for what can you build with a streaming system. This is the solution that IBM built for the NSA to process all audio and video from everything that the NSA does. So it has, insane performance, never drops data, extremely scalable, but it's also IBM. You will pay forever and ever to be able to run on top of it. And in the open source world, we believe in collaboration and not paying for things. So Apex kind of has an interesting origin as far as the other technologies out here, in that both Storm and Flink kind of came out of research land. And Apex was really a product built for businesses that became an open source technology. And what that means is that their focus was different. From the ground up, it was built for reliability and strict processing semantics, rather than just focusing on performance or buzzwords, right? They needed to build a product that other people could use, and that really shows. Now, the key kind of message I want to send here is that Apex just works, and it doesn't just work as far as building a toy application. It works when you try to take that toy application and run it 1,000 times bigger on a cluster, and it still just works without kind of these unexpected surprises. And its key strengths are dynamism, scalability, and the way in which it handles failures. And I'll dive into all 3 of those. Its weaknesses, and this is a big one, is that it's not that easy to use. It has a learning curve. And because of its more complex architecture, right, it's closer to Storm than to Flink, you really have to kind of manually put all the pieces together. But at the same time, then you're not dealing with this curse of your high-level API. The first bit is that of the 3 technologies we've looked at, Apex is the first one that allows you to dynamically reconfigure your DAG in flight. One of the really interesting points from the Concord presentation earlier is that this is now another open source streaming platform that allows you to dynamically reconfigure your topology. I think to date, the only other one I'm aware of is KafkaStreams, and I'm happy to be wrong there. These things move quickly, and it's hard to keep up with all of them. But you can both adjust the connections within your topology, so how operators connect. You can adjust the applications that you deploy without influencing other applications. And you can adjust the number of physical partitions processing your data. Apex integrates natively with Yarn, and so essentially everything is just nicely packaged within Yarn. This is very much kind of your standard architecture diagram. The thing that I want to point out that really matters is how operators are located within nodes and within threads. So here we've got two operators in the same thread. We've got another operator by itself within the same container, but in a different thread. And then we've got some operators in a different container. And now this isn't an arbitrary distinction in Apex. This is actually a configurable thing. You have the option to say, hey, I want these processes to be thread local to each other, meaning they execute in the same thread, or within the same container, or on the same node. You also have the ability to say, I want these to be in different containers, in different threads, in different nodes. And what you're really doing there is you're making a trade-off between performance and durability. If everything's in the same thread, if you've got an error or a failure in one of your operators, that's going to affect everything in that same thread. But if these are in different containers or in different nodes, then you're protected. At the same time, if you're within the same thread, then you're not paying the cost of inter-process communication or network latencies. Now this last bit, right? We talked about this notion of having 3 parallel pipelines all doing the same thing. In Apex, there's a unique thing, and that is this buffer. Formally, it's called a buffer server. But this buffer server acts as an in-memory blocker between any two physically separated containers. And what this buys us is that when you have this failure, errors do not propagate. Its failure handling mechanism is very similar to Flink's, with the exception that it has the buffer server in the loop. So it only needs to roll back to the previous checkpoint. And that's, again, a configurable thing, and it's configurable on a per operator basis. So for the first time, we have a system in which we can build applications where you can make trade-offs between durability and performance as a function of configuration. This paradigm lets you make applications that you can deploy without having to run multiple applications doing the same thing. You run one application, you can run that same application in different clusters if you want even more redundancy. But keeping this entire system running turns out to be a lot easier. And I already spoke to this, but Apex supports dynamic scaling of how much data it's processing. And this scaling can happen both manually through user input at runtime, or automatically through stat trackers that you define within the framework. So to that, it's kind of the best, but it's hard to use, right? You can fine tune your data flows and your creation of your DAG to optimize performance and to optimize for durability. They have a really good UI that lets you see kind of all the nitty gritty of what's going on in your system in terms of memory usage, CPU usage, IO, where you have backups, et cetera. It has built-in back pressure. But there is no high-level API yet. That's something that's in progress. There's no machine learning support like Flink has with Flink ML. There is a learning curve, the same one associated with Storm, more or less. And it's built for business. It's not built for simplicity. It's not just something that you can pick up and use right off the bat, but it is something that you can build a product on top of. And that turns out to be really useful. So the last bit is that I've talked a lot about streaming, but there's kind of more to it than that. I haven't touched at all on this notion of state. And state does matter in streaming systems because you're not always going to be only dealing with in-flight data. And kind of the key questions here are, what if I need to persist this data across operators, but retrieve it quickly, and then do analytics and build machine learning models, for example, on top of this data to actually give me useful insight? And why do we want state? The answer is that these are complex problems that we're trying to solve. Say we want to look for anomalies in your spending if we're trying to build a fraud detection system. We want to be able to track your spending over time, and we want to be able to persist that data, but we also want to be able to query it very quickly. We want to be able to do statistical aggregates to understand whether we're seeing anomalies in this data. We want to be able to train machine learning models so that we can close the loop and quickly deploy updated models that more rapidly reflect changes in the ecosystem or the environment that we're monitoring. And we want to be able to support cross-operator communication because all of these streaming systems partition data, but at some point you might want to unify this data and group it and make insights across a range of data. And these are hard things, right? And there's not really a good solution out there that I'm aware of in the open source realm. It really brings us to kind of this idea of distributed in-memory databases. And there's a number of them out there. There's ScyllaDB now, there's Geode. Redis has been around for a while, MemSQL, Ignite, Hazelcast, and DHTs, which exist in computer science world in general, but not really implemented in a complete fashion for having this distributed in-memory store that lets you persist data, but lets you also respond to queries quickly and scalably. And these databases are hard to build because when you're dealing with memory, memory is volatile. If you have a failure, that data is gone, right? You're not going to be able to just reread from disk once your machine reboots. This means that you have to replicate, and when you have to deal with replication, then in a distributed environment, you run into the cap theorem, right? And it's harder to guarantee consistency, availability, etc. And memory is ultimately still a pricey thing, and it's a limited resource, which makes it hard to build systems, that you can just kind of go to town on with the way that you can build and MapReduce clusters and run them on commodity hardware at massive scales, right? That was the whole idea. We can run 10,000 node clusters for pennies. So with that, that's all I've got. If anyone has any questions, I'm happy to dive into any and all of these ideas more.
So it's a great talk, and thank you so much. One dimension you haven't mentioned that is the if you're adopting one technology, for example, if I'm using batch for using Spark, for batch processing, ETL, machine learning, all that stuff, and all of a sudden come to streaming says I decide to choose something else, and then all of a sudden my top technology stack is so how do you solve that problem?
Great question. We all heard that. Basically, how do you deal with the fact that sometimes you're gonna want to do both streaming and batch? And Flink and Apex, for example, will let you simulate batching, right? Because of the windowing mechanisms that they have, you can aggregate data over time, but then you run into the notion of aggregating data in your memory, right? You essentially at that point need to persist state. You run into the challenge of how do you build an efficient machine for holding your state that you can then do analytics on. That's kind of one answer. The other answer is you take the Google Beam model, right? Or Apache Beam, and you have multiple systems tied together. But when you have multiple systems, then you're dealing with more complex infrastructure, right? There's more room for problems. Some folks have argued that streaming is a strict superset of batch, and you can, if you have enough hardware to throw at the problem, that's kind of true. But there's not, sadly, a truly good answer for that yet. I think we're moving in the direction where it becomes easier, but at the moment, it's kind of very use case specific.
You mentioned Apex is on Yarn. What about Mesos? Can it be also managed by Mesos, or it has to go through Yarn?
At the moment, it is purely Yarn-based. I think Mesos may happen in the future. It's not on the roadmap yet. I'm with you. I would like to see it on Mesos as well. It would be nice to have that flexibility. Mic's off. Yep.
Okay, all right. So the Apex on Yarn, so is a long-running Yarn container in that case?
Good question. No. So in Apex application, each operator will run configurably in a different container, essentially. Right. By default, every operator will be in its own JVM, so its own Yarn container. But because of the locality configuration that you can specify when you're creating your topology, some of these operators will be condensed within, for example, a single container, right? So this kind of lets you make that trade-off programmatically between, in Storm, you kind of have no control over what happens. So if you want things to run independently so that you can debug easier, or so that failures don't cascade between different tasks, you can't do that. In Apex and in Flink, you have some level of control over that. There is a startup cost associated with Yarn. There is a startup cost associated with recovering containers when they fail in Apex. So Apex is a self-healing system. Anything that fails, including the application master and the app manager, will recover. It does take time. Now, the one thing that in Apex we have that we don't have anywhere else is that when you do have a failure, it doesn't affect the rest of the system. these failures do not cascade in terms of either, other operators shutting down or in terms of the actual data processing itself. The one exception to this is that if the app master, the actual process that communicates with Yarn and does the research negotiation goes down, in the current version of Yarn that they run with, all the operators in the system will shut down. So that's kind of the one caveat. But that's a Yarn problem. That's not a Apex problem. In newer versions of Yarn, you can get around that, but it doesn't currently support that.
Last question. Okay, looks like
Thank you.
we ran out of questions before the last question.